Welcome to the Valar Atomics Smoking Lounge.
You started as a software engineer, yeah?
I started as a software engineer. I can't even say I really started as that though. I taught myself software engineering. I actually dropped out of high school. Yeah, this is a company I've been thinking about for a long time. 10 years, since I was about 15 or 16, I've been planning this pretty meticulously. This is actually a look inside the Ward Zero core. This is very exciting. You came on a great day. This is actually normally not open, just during our refueling operations, so you get a real look inside. Nuclear has a bad reputation, and this is part of fixing that, right?
I've seen you dub this the new atomic age. Can you explain what that means to me and what it could unlock?
We want people to see this and be inspired, and I think we've accomplished that.
What is the ultimate industrial goal?
We believe that Valar Atomics will build tens of thousands of nuclear reactors over the coming decades. Long term though, we think we can power the world.
This is probably one of the biggest and best come-ups of like a high school dropout of all time.
I think Mark Zuckerberg might have me beat, but...
Now you were in the White House.
That's right, this is really exciting. So the Trump administration really just gave us an incredible mandate, which is...
And can you just say build baby build and point to the flag?
There you go, build baby build.
I love that. That is very cool. What's in your way, Isaiah?
I would say the biggest thing that has been in our way up until maybe the last year was all right, well, welcome to Valar Atomics. Let's get some PPE on.
Good idea.
Quick.
Oh, hell, you're getting the full experience. Do these twist on the back?
Yeah, it'll twist to tighten. All right, let's go out this way.
Let's do it. Amazing.
I'm going inside a startup called Valar Atomics, a company that Isaiah Taylor dreamed up when he was only 16. A decade later, he has a team building a nuclear reactor prototype.
Is this the one that's going to the Philippines?
So we're basically doing a complete rebuild of this in the Philippines. Let's see if I can actually figure out how to unlock this.
It is a long weekend, so maybe it's not working for me.
His company has a research contract to build a real small modular reactor in Southeast Asia. And this is exactly what it will look like.
So essentially what we did is we built a full nuclear reactor. And the reason that we did this is we want to prove that it's possible to build a nuclear reactor in under a year. Now we did everything except put uranium inside of it. It would actually take longer to do the licensing work to turn on the reactor than to build the entire thing. And that's what we kind of set out to prove, is that you can actually build nuclear very quickly. So what we're looking at here is Ward Zero. This is our non-nuclear prototype reactor. This is about 100,000 pounds of steel and graphite in the main vessel over here, and this is where we simulate a nuclear reaction. So in order to simulate a nuclear reaction, essentially what we do is, instead of uranium, we use silicon carbide. Silicon carbide is a strong electrical resistor, and so we pull about 12 city blocks worth of Los Angeles power off of the grid here, run it through this core, and it'll actually get hotter than a nuclear reaction inside that core.
How hot is that?
So that's we can get this up to 2000 C in the core actually. Now, uranium centerline temperature during operation is not going to get that high, which means we actually go hotter than a real nuclear reaction. And we get to test all the systems against that heat profile.
So this one here is a test, or this will become an SMR?
This is a test model. So essentially what we do is we test all the systems, we check our helium leak rates, we bring it up to pressure, above temperature, these sorts of things. And then we essentially rebuild the system one-to-one in the Philippines. We'll build it one-to-one in other places as well. But this allows us to make sure that we got everything right, operate all the systems and make sure that we made good choices in the manufacturing and fabrication, and all of our tolerances are correct and that sort of thing.
And that's the modular point, right? Is that
Exactly.
It's easy to recreate once you have it down the first time.
And it only took us about 4 months to fabricate this the first time.
Oh, that's quick.
Yeah, so we designed it in about 6 months, brought it through engineering, procurement, and then it was a 4-month fabrication period. When we go to do it again, we think that'll come down to maybe 2 months. And in the long term, we want to be pumping these things out, every couple of weeks.
How many do you plan on building long term? What's the goal for the gigasites?
I mean, thousands, right? Per site, we'll probably climb into the hundreds, and we'll have many sites all around the world. So, we want to make thousands of these.
And do you mind me asking, you named this after your grandfather, great-grandfather?
My great-grandfather, yes. Named this after my great-grandfather, Ward Scott. He was a nuclear physicist on the Manhattan Project, yeah. So this is a bit of a nod to him. So we're building 4 reactors in succession. Ward Zero, which is this, our non-nuclear prototype. We're also building Ward 1, 2, and 3. These are essentially increasing power and sophistication, Ward 3 being our final commercial model that we go build lots of. Yeah.
So your great-grandfather worked on the Manhattan Project?
He did, yes. He was recruited when he was 22 to work in the secret city, Oak Ridge, in Oak Ridge, Tennessee, yeah.
And now you're working on a nuclear reactor. Like, it kind of lost its way, and now you're bringing back the new atomic age, right?
I'm hoping to. You know, I think that nuclear was this incredible technology that we created in the 1940s, scaled out a little bit in the 1960s, and unfortunately came to a halt in 1979 in 3 Mile Island. We essentially stopped building nuclear in the West, at least in the United States, in 1979. And we missed a lot of years, right? There's a lot of technology that we could have developed, we could have continued marching forward, making it safer, making it even cheaper. And unfortunately we stopped. So this is a bit of a revival.
There's a lot of fear around it, though.
Yes, you know, every technology has a risk profile, right? If you're generating power, if it's coal, if it's natural gas, even solar, there's a certain death rate associated with power, right? Now, the right way to measure this is how much power do you make and how many deaths are there per unit power. And if you actually look at it that way, nuclear is by far the safest form of energy on Earth. It's even safer than solar. So people don't realize this, but even solar has a casualty rate associated with it. Unfortunately, everything does in the real world. And
is that typically in development? Like,
it's an installation, right? So people installing solar panels on roofs, and there's injuries associated with that. And then in the material sourcing and the mining as well. So, nuclear actually just has a smaller physical footprint. We don't use as much physical material, as much mined material, and it's actually much safer because of that. So if you really look at the numbers and look at this from a scientific perspective, nuclear actually is the safest form of power generation in the world.
So Elon's wrong?
Elon, actually I've debated with him about this on Twitter. He sees sort of the long curve of civilization and extracting huge amounts of power from the sun. And it's hard to argue that the sun won't be the dominant source of energy in the solar system over, let's say, 10,000 years. But I look at the next 100 years and I say, how are we going to power the industries of the future? How are we going to power AI? How are we going to power advanced manufacturing? I think those things are going to come from nuclear fission. Also, as we get into space exploration, the further you get away from the sun, the harder it is to harvest solar energy. And nuclear doesn't have the same constraint, right? So I think this is definitely a very meaningful piece of the future over the next couple hundred years.
Can we get closer to it?
Let's do it.
Amazing.
If you've seen the movie Oppenheimer, you'll know what Isaiah is talking about. Nuclear fission is when energy is made by splitting atoms. It was first discovered in Austria in 1938, and the first reactor built in America in 1942. It was quickly weaponized, including in America's secret Manhattan Project. And we know what happened next. But Isaiah believes fission can be rebuilt and operated safely at scale to significantly reduce the cost and availability of energy. He plans to build gigasites across America with thousands of these small modular reactors powering industries.
But these are 3 modules that work together. We have the heat transport system that we're looking at right here, the main reactor body in the background there, and then this is actually the control center. So you can kind of look at the heat transport system. You'll notice that everything is very open and very modular. We've made it extremely easy to work on, right? Maintenance is an important aspect here. We want it to be easy to work on the reactor, to keep high uptime, especially if we want to serve data centers and these sorts of things that need high uptime. You want it to be very maintainable. So we thought very hard about how do we position things and how do we orient things to make it very easy to go and do maintenance.
So this might be a normally naive question, but an SMR is all 3 parts, 1, 2, 3?
Yeah, so we break this into 3 modules. Some people, work to make the entire box a single reactor, right? They want to put a whole reactor in one box, including the heat transport, including power conversion, those sorts of things. We think it's actually more logical to break these up a little bit. You'll notice that all 3 of these are actually built into ISO frames. So they're built into essentially the shipping container spec. You can actually put these anywhere that you can put a shipping container.
So that is exactly a 20-foot TEU?
Correct, yes. Literally to the exact spec, including the corner blocks down there. Which means, anywhere that you can mount a shipping container in the corner block configuration. You can even see the forklift tracks underneath there as well. So
is that actually a repurposed shipping container, or you've just purpose-built that to that size?
Purpose-built it to the ISO 668 spec, so anywhere that you can put this truck, train, ship, airplane, you can put one of these, so.
That's
pretty
insane.
fun.
That's really cool.
This helps us a lot for testing. Let's check out the control center as well. The control center is pretty fun.
In his mind, nuclear is not just becoming the future, but needs to look like it too.
Oh my God. This is like a gaming studio.
So this looks a little bit different than a normal nuclear reactor control panel, and that's very purposeful. If we're making a nuclear reactor in the year 2025, it should probably not look like an operating panel from a hospital from the 1960s, right?
The aesthetics, the effort, I so appreciate that.
We went to a lot of effort to this. You know, we really want people to fall in love with nuclear. We want them to see it as something that powers the future and something that they're extremely excited to be a part of, and so that's what we've tried to do here.
In New Zealand, we import a lot of coal because we have what's called the Hurley power station that has coal-fired Rankine units.
Yes.
We have a run out of gas.
Yep.
And we have renewable energy for everything else, but on an industrial scale, gas and for residential is still required. So what solution does your SMRs potentially provide, not only in creating energy themselves, but also creating synthetic fuels?
Yeah, so we would look at, you know, the coal, the off gas from that coal plant essentially, which is currently adding CO2 to the atmosphere, right? And we essentially capture all of that flue gas and we would convert it directly to either liquid fuels or even natural gas. So we can essentially replace a gas supply, replace liquid fuel with, you know, the emissions of a coal plant.
That almost eliminates the cost of energy.
Correct. It also completely eliminates the climate impact as well. It essentially means you have a carbon neutral coal plant.
So remind me why nuclear is banned again?
Nuclear has a bad reputation, and this is part of fixing that, right? We want to show that this thing is really, really cool and is an exciting piece of the future to be excited about.
But it definitely requires a safety and cultural revolution and understanding, yeah?
Absolutely, and you know, the safety aspect, I think what's most important is you want to actually build plants often and you want to iterate and innovate, right? So how do we drive down the safety curve in a technology? Take cars, for example. Cars are a lot safer today than they were 60 years ago, right? The death rates on a car crash are far, far lower than in the 1960s. And what has driven us down that curve is innovation. And the way that you drive down that curve is you continue making new models and making them better every year. And so a safe nuclear industry is a nuclear industry that continues making reactors and makes them often, and it also makes them smaller in a repeatable format because it's actually easier to innovate, right? If your reactor is something that you produce every week, you're constantly looking at it, figuring out how do you improve it, how do you make it safer. So innovation is going to drive that safety even more than, you know, trying to sit there for a very long time and create the perfect piece of paper that describes a perfect nuclear power plant in theory. It's actually better to make a small reactor that's very safe and make many of them.
Valar was undergoing a test refueling operation the day I was there, and in true Gundo startup style, the team had been working all weekend.
And here's some of the team. Hey guys, how are you? I feel like we should add, since we're filming you guys, that like today is a public holiday and these guys are in here hustling, so solid.
Yeah, I mean, it's like, every day is the exact same. We just work every day. So you wake up, work here till 1 in the morning, go to sleep. Like,
Oh my God.
So we are in an active refueling operation right now, which means we're unloading all of the fuel blocks out of the core and timing ourselves to essentially see how long does it take to do a full removal of core blocks, fuel blocks from the core and reloading them again. These are the fuel blocks right here. So uranium is going to be embedded in some of these fuel holes, and some of these holes are also open for cooling channels. There's a combination of helium flow through these blocks and embedded uranium compacts.
Where are you going to get the uranium from?
So our uranium is really off-the-shelf stuff. You know, a lot of nuclear companies that are started today need HALEU. Say, what's up? No, you're fine, yeah.
No, you're good.
We're just having fun.
We're in your way.
Yes, so, you know, HALEU's in big demand today. People want HALEU, it's an advanced fuel. We actually just use low enriched uranium. It's off-the-shelf stuff. You can get it anywhere. Ours comes from Framatome, but you can really buy it anywhere in the world. Low enriched uranium actually currently powers about 7% of global electricity today. So we like taking things off of pre-existing supply chains, which are, you know, very large and abundant.
What's the price of uranium doing these days?
It's going up. It's going up, but you know, uranium price actually doesn't affect overall LCOE of nuclear too much. You know, uranium is actually quite cheap compared to the power that it makes, and these industries are very easy to scale up. So we can scale up enrichment capacity, we can scale up mining. This is one of those commodities that, you know, as the price goes up, people realize that it needs to be, you know, drilled and explored more, and it comes back down. And so, you know, uranium is truly abundant on Earth. There's enough nuclear fuel on Earth today to power current humanity's needs for about 40 billion years. You know, few people actually realize how much uranium that we have access to. So yeah, this is a fuel format for the future.
This next part is wild. Isaiah took me atop the nuclear reactor to stare into its core. Don't worry, Mum, this is just a prototype.
Whoa!
This is actually a look inside the Ward Zero core. This is very exciting. You came on a great day. This is actually normally not open, just during our refueling operation, so you get a real look inside. So what we're looking at here is three elements. We have the nuclear core itself. This is this stack of graphite. All the blocks that we're looking at down there that you filmed a moment ago were inside here a day ago. And those are the main fuel blocks. We also have the graphite reflectors along the outside. And then we have the graphite base at the bottom as well. All of this is stacked up inside the core barrel. So you can see on the inside here we have what's a stainless steel 316 barrel. That's essentially the heat shield for the reactor. And then we have another vessel on the outside. That's our big, thick, heavy carbon steel outer RPV. That's what holds the pressure. So under pressure, this will hold about 4 MPa, megapascal of helium pressure. And inside the core here, it'll get up to about 1,000 degrees Celsius. So there's a lot of heat and a lot of pressure in this thing when it's running.
But you said it could get to 2,000.
So we can get the heaters to 2,000 to do extreme high temperature testing. In actual nuclear operations, it'll stay below 1,000.
Wow. It is pretty small. Like, it's not enormous.
Yes.
I mean, compare it to something like a rocket, it's, kind of like half the size of an upper stage.
That's right, yeah. And that's part of the purpose here, right? If you build them smaller, and we build larger reactors than this, the next model we'll build will be about 1.7 times the diameter, so you can kind of imagine that. But it's still pretty small. And the reason that we do that is that it's actually easier to manufacture smaller things than massive things, right?
Of course.
In industrial capacity that we have today, especially in the West, we're really good at making things about the size of a bus, right? About the size of a bus is like our sweet spot for, making lots of a thing. And we think that applies to nuclear as well. We get to use a lot of the tools off the shelf that other manufacturers get to use, and that's super important to make sure you have a robust supply chain.
And can you just say build, baby, build and point to the flag?
There you go. Build, baby, build.
I love that. That is very cool.
Yeah, this is a sick view.
This is insane.
I could stand here all day.
I bet you could.
The graphite is beautiful.
What sort of robotics are you using? Is this like a crane to
That's right.
pull it out?
Yeah, so this is our crane for refueling the core. So all of the blocks come out on this crane right here. We've got it. Part of what we're doing today is we're doing operations testing to see how quickly we can load and unload the core, right? We want to see during normal operations how efficient is it, to pull all the fuel blocks out. And it's actually going incredibly well so far. We wanted to be able to do an entire refueling operation in the course of a week, and it looks like we're going to significantly beat that.
Wow, that's awesome. How do you feel staring at this? Proud, or do you look at this going, there's work to do?
There is work to do, but I'm incredibly proud of the team. I mean, we really, I think, shocked the world by building this in the timeline that we built it. We went out and we raised a very small amount of money, a very modest amount of money, and said we're going to build a full nuclear reactor in under a year. And we actually built it in 10 months. So I'm unbelievably proud of the team. We pulled people with 25 years of experience building this type of nuclear reactor and convinced them that we have the business model that's going to win. And we're able to get just an incredibly talented team with a lot of experience. So they've moved extremely fast.
I wanted to put his team's other talents to the test.
How good are you guys with hands? Who's like the baseball player among us? Can one of you catch this? Are you sure?
Yeah.
All right.
Fair to say the Valar team can add camera work to their CVs.
Thank you so much. You can throw a cameraman on your
Thank
CV.
you. I appreciate
Thanks so much, guys.
One more
Awesome.
kind of cool thing to see here is the thermal insulation underside of this is some incredible, incredible handiwork. Just go ahead and put the camera underneath there.
Oh, wow. That's
Yes.
beautiful. It's like a spaceship.
Yes, so this is thermal insulation, and the reason it's shiny is that it actually reflects IR, right? So when we're producing a lot of infrared heat from inside the core, the shininess is actually, it's a photon spectrum, right? So we're actually reflecting it back down. And then we also have insulation inside of those blocks as well. But this is some very, very fine handiwork getting this to come together, and it looks pretty cool.
This must be a different type of engineering though, right? This would be quite specialized compared to just like...
That's right.
Yeah.
It's very specialized, and the interesting thing about nuclear is that there are a lot of specialties, right? So we have people here who have touched every type of engineering discipline. It's one of the reasons that we're in Los Angeles. Los Angeles has engineering disciplines from almost everything you can think of, from thermal hydraulics to aerodynamics to instrumentation and control to combustion to chemistry. Everything that goes into America's high-powered industries happens here in the South Bay, so that's why we're here.
What is that a result of? Is that because SpaceX is in LA?
In the 1930s and 40s, the United States essentially picked South Bay, Los Angeles as the place for the aerospace hub, right? So Howard Hughes was here, right, in Hughes Aircraft, and Jack Northrop, all of the early aviation guys picked South Bay, Los Angeles to essentially scale out our military industrial base. all of those skills have accumulated over time, and we have an amazing swath of companies that have decided to build incredible things here. SpaceX, obviously, Anduril's here as well.
But there's also Boeing, right? To your point of aircraft.
Correct, yeah. We got Boeing here, there's Raytheon here, Lockheed Martin down the road, those sorts of things. So yeah, incredibly talented people that have been working on bending metal and making it hot for a long time.
Isaiah says his company will probably stay private and do, quote, the SpaceX thing. So I wanted to know how they're privately funding this mission and breaking down regulatory barriers. And of course, the aesthetics are just as good for the interview location.
Welcome to the Valar Atomics Smoking Lounge.
This is amazing. Thank you so much for having us in. And I'll remind everyone that I DM'd you on X this morning, and here we are on a holiday. So thank you so much.
We like to move fast. We stay in the seat. We always keep trucking, so absolutely.
Now, you were in the White House.
Yes.
Last week.
Friday. It's been a blur, but yes, on Friday.
Announcing with the governor of Utah that they plan to build a test reactor there. Tell me about that plan and how quickly you could achieve it.
That's right. This is really exciting. So the Trump administration really just gave us an incredible mandate, which is we haven't built test reactors in this country for almost 40 years now. And that's a shame, right? We invented nuclear energy in the United States. We created the world's first nuclear reactor. We basically have piloted every major reactor branch and architecture. And in the 1970s, we essentially stopped. We stopped innovating. And so the mandate from the Trump administration is, let's turn one on by July 4th, 2026, which is America's 250th birthday. So we're going to have a birthday celebration, 250th, with christening a new reactor and hopefully splitting atoms for the first time. It's a very aggressive schedule, but I think the Valar Atomics team is ready to meet it.
I've seen you dub this the new atomic age. Can you explain what that means to me and what it could unlock?
The new atomic age is all about fulfilling the promises that we had for nuclear energy in the 50s and 60s. If you go back and read the literature at the time, we were trying to grapple with this idea of fundamentally cheaper energy. Like, what is the world going to look like when energy is maybe 10 times cheaper than it was at the time? And that world was very exciting. We thought about cheaper food even. Like, there's things that you wouldn't even think of, but a lot of our food cost comes from the cost of synthetic nitrogen, which is essentially the cost of energy, right? Because we use natural gas in the Haber-Bosch process to make nitrogen for our crops. And we were thinking about manufacturing, and we were thinking about chemical production, and what are the materials in the world going to look like when we can produce them at a fifth of the cost of today. And a lot of those promises died out in 3 Mile Island, right? There was this one nuclear incident in the United States that essentially shuttered the industry, and all of those dreams kind of died out at the same time. So this is about rebooting that. But I would say it's even more exciting than it was in the 60s, because a couple of things have happened. One is that manufacturing has become even more advanced. Energy is becoming the primary key, right? So if you look at what does advanced manufacturing do, it goes from mostly a highly skilled labor type role where you have people trying to do the same things over and over in a repeatable fashion, to robots and machines doing the same thing over and over and trying to scale those out. And those machines fundamentally just need energy, right? So the input into manufacturing is becoming energy and raw materials. But even if you think about raw materials, that itself becomes an energy cost, because you're running trucks to do the mining, and you're running machines to crush the ore, and then chemicals to do the refining, and all of those are energy costs as well. So what we're looking at is energy becoming the fundamental input to goods, and that energy getting cheaper. And so what we're moving toward is really an era of abundance. We're looking at the cost of the physical world around us becoming lower, which is amazing, right? Every time that we get cheaper energy, humans end up living better and living longer, and I would say more exciting lives. I like jet aircraft. I like driving very fast. These things are a lot of fun, and they all take energy, so we're really excited about that.
That should ultimately, if you're successful, result in a deflationary environment, because goods should only cost what they cost to produce.
Absolutely.
And if the cost of energy to produce anything, whether it be a car or food, with nuclear could be close to zero?
I mean, we push it close to zero. I'd say the goal of Valar Atomics is to make energy cheaper every year that we operate, continuously, forever. And I think that that's a very achievable goal. I mean, energy is abundant in the universe, and you just have to unlock it. And yeah, that is massively deflationary. And I think you look around today, and governments all around the world are trying to figure out how to not spend so much money and not inflate their currencies into infinitum. And one of the ways to do that is to just make things cheaper, to use production to actually promote abundance and flourishing. And I think a lot of people are looking to private industry to do that. If Congress is not able to cut spending, well, maybe at least we can outgrow them, we can outbuild them. And so yes, I think Valar Atomics will be a huge part of that.
What's in your way, Isaiah?
I would say the biggest thing that has been in our way up until maybe the last year was regulation, right? I think that we massively over-regulated the nuclear industry somewhat in response to incidents like 3 Mile Island. Back up to when nuclear regulation was written, we were essentially trying to protect an American monopoly around this technology, right? So we were the only ones in the world who were really building it at scale. The British started doing it, the Soviets figured it out, but we were very concerned with how do we protect the power of the atom? How do we keep this to ourselves? And unfortunately, all the red tape and all the barriers that we added ended up slowing us down, and it didn't slow anybody else down, right? So now where we are today is, I would say, a dangerous position, right? China is building 28 nuclear reactors right now. We're building 0. Right? Russia's building nuclear reactors all over the world. They're building them for South America and for Africa. And we have to face a question, which is, who do we want building the global nuclear infrastructure? Do we want the West to build it? Do we want the United States to build it? Or do we want our rivals to build it? And so I think that there's this reckoning to say these really strict rules that we put in place really slowed us down more than it slowed down anybody else. And so it's time to roll those back.
Is that why you took legal action against the NRC?
Our legal action against the NRC is quite interesting. When Congress first passed the Atomic Energy Act, this is Atomic Energy Act of 1946, they essentially gave the federal government carte blanche over everything that splits an atom, right? So if it splits an atom, it's under what was at the time the AEC. In 1954, they actually rolled that back a little bit. And they said, you know what? There's a class of reactors that the AEC doesn't need to regulate. And this class of reactors is small reactors and safe reactors, and ones that are not large enough or dangerous enough to affect the health and safety of the public or the national security of the United States. And the reason that they did that is that they wanted to allow innovation, right? And they recognized that the federal government is good at creating guardrails for very mature industries, right? It can create a guardrail for a large company to do something 1,000 times, right? But it's not so great at creating regulations that allow startups and smaller companies to do innovation, to learn new ways of doing things, right? And unfortunately, the AEC at the time, has since become the NRC, it was called the AEC at the time, essentially ignored that mandate from Congress. They didn't change their rulemaking around that new statute, and they continued to claim jurisdiction over every single thing in the United States that splits an atom. And so our lawsuit challenges that and says, you need to abide by the law of the Atomic Energy Act and create this class of reactors which is outside of the jurisdiction of the AEC. And our 5 co-plaintiff states that are in the lawsuit with us all want to accelerate nuclear, and they want to allow us to innovate, right? That's the most important part, is they want to provide, stretches of land out in the desert where you can do a very small, very safe test and gather data, right? Because data is how you learn, data is how you improve, innovate, make it safer.
If you don't mind me saying, it's pretty ballsy. 16 months in to this business for you to take legal action against a regulator. I know that there are others with you, but that's a big move. A lot of great companies, though, started with suing the government.
It's true. I wouldn't say it's a well-worn path, but a few people have pulled it off. Yeah, this is a company I've been thinking about for a long time. Really 10 years, since I was about 15 or 16, I've been planning this pretty meticulously in how we'd go about it. And one of those actions, was we need to actually make the regulators get in line with the congressional mandate, right? And a lawsuit is a great way to do that. Advocacy can do it as well, and you're seeing some of that today. You're seeing some of the executive orders that came out. So there's a lot of different, pieces of pressure applied to the regulator to make the system actually move faster again and turn on nuclear reactors. We're a 16-month-old company, but the experience here around the table in the team, makes up over 100 years of combined experience in nuclear energy and actually building reactors all around the world. So we're ready to move.
Wow, that's really niche experience that you've managed to pull in.
Yes, we've really pulled some of the best people in the entire world in nuclear who, will know more about nuclear reactors than I'll ever forget in my life. Yeah, I'm incredibly grateful to this team.
You started as a software engineer, yeah?
I started as a software engineer. I can't even say I really started as that, though. I taught myself software engineering. I actually dropped out of high school. But I worked in software engineering for a while and started a couple of companies as well.
This is probably one of the biggest and best come-ups of like a high school dropout of all time.
I think Mark Zuckerberg might have me beat, but yeah.
You wait, Zuck.
That's right. Just wait.
What is the ultimate industrial goal? We've just seen one of your test reactors in the factory. You are going to build another in the Philippines.
That's right.
But that's going to be one of what, hundreds, thousands at these gigasites around the world?
We believe that Valar Atomics will build tens of thousands of nuclear reactors over the coming decades. And if you think about what do we do well as a civilization, as an industrial society, we do things really well that we do often, right? So we're really good at making tens of thousands of things or even millions of things. And we're actually not that good at making, small numbers of things. We don't make ships nearly as well as we make iPhones, right? So if you want an industry to be mature and you want it to be cost effective, you need to make a lot of it. And making a lot of it allows you to do a few things. One, it allows you to get the repetitions down to make sure that you've got that system perfectly tuned. It also allows you to innovate though. And so you'll notice, when we were out there before, our reactors are quite small. There's a couple reasons for that. One is that smaller reactors are fundamentally safer. There's a couple of basic properties of physics that make that the case. But the other thing is that when you're building a small unit over and over, if you want to make a change to that unit, how you're making it to make it a little bit safer, to make it a little bit better, it's a relatively small change in tooling to go and improve that. Whereas if you're making massive, massive units that take years to construct, it's harder to turn the ship, right? And we want to keep the ship nimble. We want it to make thousands of units and for those to evolve over time into better and better machines.
You're not the only one building SMRs.
That's right.
And there's quite a clear investment link to other small modular reactor builders with AI compute.
That's right.
Sam Altman, Amazon, I think maybe even Microsoft has invested in another company too. How critical are SMRs specifically for fueling AI demand?
I think that SMRs are one of the only credible ways that we actually can move forward in the AI race. If you look at all of the other forms of power generation out there, they're very limited just in basic supply chain constraints. It's actually hard to build new nat gas at this point. And if you actually look at the prices and the timelines for natural gas generation to try to fuel the AI demand, a couple years ago, we were trying to move away from natural gas and trying to go full renewables for data centers. And since then, we've realized, well, we just need power wherever we can get it. But even if you look at these traditional forms of power, they have very long lead times and they're becoming expensive. And I actually think that SMRs are positioned to be faster and cheaper than existing supplies of energy just because it's brand new and because people like me are sitting down and thinking about it from first principles and saying, how do we actually build this machine that we build hundreds of and then thousands of? And can we put gigawatts of power down into the grid in a very short amount of time?
What else could this fuel? What other industries, industrial scale industries, do you see this being a big part of in the future?
Yeah, so we see Valar Atomics as initially becoming the industrial powerhouse of the world, right? So we want to make the world's industrial energy. Artificial intelligence is a huge part of the early story, but we want to move into advanced manufacturing, robotics, anywhere that you are turning physical goods into end products using energy. Valar Atomics is a great place to plug into that. Long term though, we think we can power the world. How do we do that? Well, one way is that you go and build lots of nuclear power generation stations all over the place. And we think that will happen eventually, but an even faster way to do that is to actually make synthetic fuel. So this is a little bit of a mind bender, but the current way that the globe gets most of its fuel is through hydrocarbons, right? We move huge amounts of hydrocarbons all around the world, and that's how we get most of our energy. Well, there's two ways that you can get a hydrocarbon fuel. You can dig it out of the ground, right, which is a little bit dirty and you have to filter some stuff out, and then at the end of the day, you're adding CO2 to the atmosphere. The other thing that you can do though is you can build it, right? So you can take CO2 and you can take water. Those have all the ingredients that you need to make a hydrocarbon. You can make jet fuel from CO2 and water, gasoline, diesel, even natural gas. And all you need is energy. Essentially, you need enough energy to split water into hydrogen and oxygen. And then hydrogen, when you combine it with CO2, will make a synthetic fuel. So when we look at that, we say, well, essentially what we're talking about here is very, very large scale energy distribution rails. You can kind of think of the hydrocarbon infrastructure all over the world as like an alternate energy grid. And it's actually a huge energy grid. It's most of the energy is happening through pipelines and through tanks and tanker ships. And we get to plug into that if we can make hydrocarbons cheap enough. So we see our Valar Atomics gigasites as eventually making synthetic fuels, making them cheaper than refining oil, and then exporting them through the pre-existing railways of distributing hydrocarbons all around the world.
And ultimately making OPEC obsolete.
Well, yes, that is one of the downstream implications, is that the United States gets to make hydrocarbons wherever we want, and we get to make it for our allies, and our allies get to be energy independent, which is really, really critical in some regions of the world.
Oil industry should probably be investing in you.
That's a great idea. I think you're right about that. Absolutely. Yes. I mean, I think this is the future. Like, we're long hydrocarbons, right? We think that hydrocarbons are going to be around for a long time. There's a huge spectrum of industries that have no real plan to get off of hydrocarbons. We were talking before, jet aircraft need hydrocarbons. They need that energy density. And when you look over the next 50 years, I think it's highly likely that those hydrocarbons are going to come from us.
You effectively have a solution that takes us off the dirty hydrocarbon, but allows the world to stay hooked on hydrocarbon. You would just produce it at a way that doesn't impact the earth.
That's right. And I think if you look at a hydrocarbon, it's hard to come up with a better fuel, actually. Hydrocarbons are incredible, incredible fuels. I gave a talk at USC a couple months ago in front of a panel of climate scientists, and I basically showed them the periodic table, and I said, let's invent the perfect fuel together. And we started looking at all of the different elements on the periodic table and coming up with different fuels. And it was a little bit of a trick because at the end of the day, as you start working through the different combinations, you realize that a hydrocarbon really is the best fuel that you could come up with. It's very, very hard to come up with a liquid fuel that is stable at room temperature, that has the energy density that you need, that has elements which already exist in the atmosphere, right, both water and CO2. We really have stumbled on to an incredible, incredible thing with hydrocarbons, and I don't think that humanity leaves them anytime soon.
I mentioned investment already, but you just closed a 90 mil US round.
That's right.
Can you talk to me who's invested in that and if you might need more if you're going to achieve this ambition at pace?
Absolutely. We have an incredible slate of investors. Ride Ventures here in Los Angeles, amazing deep tech fund, Initialized Capital, and Ali Corp are our big investors. Love them. They are incredibly supportive of the company. I think that we're a very, very capital efficient company, right? For the amount of money that we've raised and the amount of traction that we've had, we've done incredibly well. And absolutely, I think that continues into the future. I think you're going to see unbelievable traction out of us for a very modest amount of capital.
I'm excited to see it. Thank you so much for your time. Appreciate you having us on.
Absolutely.
Thanks for watching Markets with Madison. If you enjoyed this interview, please hit the like and subscribe buttons below. I do all of the research for these episodes myself, so your support means a lot. I always love to hear your feedback and ideas, so please drop any thoughts in the comments below. Now go put your money to work.